start talking about it. So last week we've gone through week 1 notes, and I started introducing you to your building where you need to perform step-by-step computations. You don't need to use the software at this stage. I think I've asked you so far to calculate dead loads, live loads on particular areas, 2 different areas, the small one, the large one, the overall and the core one. And that's where we stopped. And Wednesday this week, we should continue from there. This Wednesday, the workshop will be online for Melbourne or Bandura campus. So if you, just to confirm how to access it, students should be able to access, only Melbourne students should be able to access such meetings via, I will show it to you. So from here, you simply go to Teams, and this section here, or this team, was the general one that we are meeting through now. This is for the lecture. The first one is for Bendigo students at their during their odd weeks. So their weeks were the odd numbers, week 1, week 3, etc. That's when they have it online. For Melbourne campus, even numbers, even weeks, 2, week 4, week 6, they can access it from this link, which should be ready for them, and the students within the right campus should be in the right team. All right, so Melbourne students can access the workshop from this link, and yeah, we can work on our projects from here as well. Any questions? Let me know. Otherwise, I can start talking about our week 2 topic. As I said before last week, week 2, we still not into the theories. Right? So there are dynamic theories that I will be talking about from week 3 to about week 11. And they are, each theory or topic will be followed by examples that we do, some of them during the lecture, and the other part will be done during the first hour of the workshop. This week, I just want to deliver the concept of computer modeling. And it's, again, still, that's not the only time where I'm going to be talking about this software. When you need to implement it and use it for your assignment 1, I will be showing you, or I will provide you with a video which shows you how to build the buildings we're working on with such software and simulate it. So we're going to talk about it. The talk will be more about the software. All right, so these notes were provided by Inductor, who have developed the software. Now, this software, it's again one of the available packages inside the suite, and the suite got different packages. Like, they got a package that engineers use to design slabs by their own, like floors, whether bad beams or flat slabs, etc. They got another packages which design post-tensioning slabs. So, you know, post-tensioning, where they got cables. It's nothing, we won't be doing these things in this subject. They got another package which does RCC and footing design. RCC means reinforced concrete columns, and footing design as well. So the main really use for this one is we're going to be modeling or simulating the building we have in assessment 1. So we're going to be using this package here, RCB. All right. Just an overview where I'm going to take you through is, what does it mean, the modeling? What does it mean? Okay. And as you can see with these 2 main points, it can be computer modeling. You do something by computer. or it can be structural modeling, where physically you may need to build that model and evaluate how it's performing. All right. So when we talk about computer modeling, we're gonna, structural modeling, we're gonna talk about the challenges. There is always challenges, which you will also face when you're gonna build your own building for assignment 1. And there is as well considerations that you have to take into account, because simply the equations which forms the software. So the softwares are really made from simply equations, really lengthy equations that we can't do it by hand because of the error you may go through, all the complication in the computation. So we use such packages to go through such assumptions, right? Simple example, you know the story behind those green color, the green walls and the non-colored walls in assignment 1, where I said we will consider the green walls to take only vertical load, not a shear wall. We have to let the software know that. Otherwise, the software will drive the analysis in the wrong way. That's what we mean considerations. All right, and this is now. That's where I said you always need someone to build those models, an engineer to build those models. You can't have, because the engineer will be thinking about the framing, the structural modeling details, and how he or she wants it to behave under structural loads, whether wind load or earthquake loads. All right, we're going to go through this kind of information and talk about more. Structural design software. So the package that we are talking about and you're going to be using, it's kind of in between simple 2D software and detailed finite element program. So I think most of you have used or know during your university course or at work, there is something, can I ask, have you used 2D softwares like structure analysis? What do you use before? What have you used so far, or any examples? ETABS, okay. What else? SAP 2000, excellent. SAP 2000, it is, if you remember, it just model sticks and nodes as far SAP 2000 structure analysis program. And locally, it's not very well known. Okay, these are 3 excellent examples that people are putting up there. What they're putting up there, ETABS, SAP 2000, if you see the chat, STAD Pro, I think 2 students mentioned them. These are really 3 excellent examples I can take you through. Now, SAFE as well for fooding, that's totally fine. But I think the 3 ones, they can take you from simple simulations to advanced simulations. What do I mean? Starting with SAP. SAP simply, what's used locally is not SAP. SAP's not used locally. We use something very, very similar to it, is space gas, but we won't be reusing it in this subject. It's a space gas. People who know how to use SAP, they should be able to drive space gas. I personally started my training with SAP 2000. It's very close. If you know the concept, you can't drive the other one, space gas. So anyway, the space gas or SAP, they are kind of a simplified simulations. They model sticks and nodes, right? They're simple. They are very fast in terms of the calculations it needs, and they can do the job. Depends on how the engineer will be considering his structural modeling. Okay, if you need more advanced technology to use and let you bypass some complicated steps, then you can go one one step forward, and here I can mention ETABS. ETABS, I can tell you, it's quite close to RCB because space gas or SAP 2000, they don't have the abilities, adequate abilities to simulate shear walls, right? And the walling system, etc., etc. Space gas is good in simulating sticks, like also it's got some, I know it's got panels, but those like surfaces to in SAP 2000. However, they won't be. Look, I'm talking about maybe now they introduce things. Maybe now they introduce things. However, the details are coming. RCB will show you the differences. Okay, there are some concept, some aspects that may not be simulated in a faster way than what SAP 2000 or Space Gas can do, right? So as I said, in the middle, like the advanced kind of simulation process can be done by RCB, and what's equivalent to RCB is ETABS. However, what RCB is kind of helpful, I can say, is the standards. It's well connected to the local standards which you're going to experience. In week 5 or 6, when I start to work on your modeling the building, you're going to see that it's very well connected to estimating the wind loads, estimating the dead loads, estimating the earthquake loads in line with the standards, the local standards, right? ETABS, as far as I know, does not really have this unless they get a developer. So someone will say me, does that mean they all can end up doing the same job? Yes, but some of them may give you better consideration than another. I can tell you about 15 years ago, we checked a tower in the Docklands that the engineers have checked its stability by using space gas, which is like SAP 2000. So it's possible for the engineers to simulate what you're learning here by space gas, but you have to correctly or as accurate as possible simulate the sticks to reflect the core structure, which we talked about, and you're going to be checking. If you manage to correctly simulate that core as a stick, and you're going to say the stick will have the correct IXX, IYY, and what I was talking to you about, you can be almost there with some safety factor, which is fine. Okay, so that's RCB. Someone talked to me about here or listed the last one, STAD Pro. STAD Pro can really be very advanced, too advanced, STAD Pro, and may not be necessary for what we're doing. Well, I mean what we're doing, designing a building as a whole, because it's going to measure a lot, and it's not really. STAD Pro, it's useful if you are investigating a connection between a column and a beam, or a column and a footing, a beam and a slab. That's if you want to look at a detail, a connection between here and there. This cannot be done by space gas or SAP. No, you can't. You know, researchers or sometimes engineers, they want to check how the connection gonna behave and all the stresses that will be resulted and strains that will be resulted. This cannot be done by ETABS. This cannot be done by space gas. This cannot be done by RCB. Yeah, so you would use something like I think with your course you are studying. I think some of you have studied already ANSYS or STAD Pro as well. Now I'm not sure. Maybe some of you had maybe worked on versions who does other things. So I'm more than happy to know that. As far as things have been used. So in summary, programs, yes, engineers need to be to decide to know what to use. It's like, you know, a builder, he needs to know, does he need what type of truck he wants, like a crane. Okay, let's say you are construction engineers, not designers, construction engineers. There are many types of cranes. but not all of them may fit the purpose of what you want to do. Maybe you want, okay, the question is, what do you want to carry with that crane? Do you want to carry some lightweight steel bars, small size patch of steel bars and boxes to put them from the truck to the construction site? Then you need this type of truck. If you want to crane precast panels, large walls, then definitely you need different system of cranes that can go higher, that can move in a different. So this is same thing. Deciding on a software definitely need to be thought about, depends on what we're doing. If you want to critically investigate a connection between a bolt or how the bolt is behaving at a connection, then none of those generic software will help you. You need to go to something like ANSYS to really work on and simulate more details. And I trust STAAD Pro does that as well, because you can model small components and try to mesh them and work on them. So first thing is, as you get into a design exercise, you need to know what are you using. Will it really do the job, or is just more over required, or it won't be really simulating or giving you what you want. The RCB, it will be, yes, local engineers use them to evaluate their hand calculations, to evaluate the designs they did through the standards and through the steps you are implementing on assignment number 1. So typically there are maybe 3 engineers, 2 of them may be doing the hand calculation processes, another one he may be doing the simulations and comparing results, because you kind of checking your work. Maybe there is some consideration, especially if the core was actually placed not in the middle of the building, things will be complicated. Because when we, like your case, your project case, you have the L shape, and your core is located not at the center of mass. So the computer will be able to calculate those irregularities and give you better reflection about such different stresses, right? Yeah, so let's go through, I think, the second slide. What does it mean? Is it just a quick definitions? Modeling, what does modeling mean? There is computer modeling and there is structural modeling. I think we have took you through these notes already. Yes, I've covered these notes. That's what we can go through. And this image really shows you, so this is what I'm saying. This is something, what we mean computer modeling, which is beyond the scope of what we are doing. And this is like ANSYS software. Can I ask the man or lady who suggested do they simulate these kind of things in them, or they more kind of more generic elements with the STAAD Pro? Have you used it before? Is it used to simulate and model? So this was just connections between a column, that's the column, and this is a beam. And engineers can determine how things gonna reflect after they are heavily loaded, after the beams are heavily happen at the connection. So these kind of investigations or designs cannot be done by softwares like RCB or STAAD, RCB or SAP 2000 or SpaceGate. You would need a high order finite limit packages. They can mesh small components inside your element, and then you're gonna investigate the stresses and strains. Okay. The other things is, unless you're gonna be practicing something else, then like I think it's different type of engineering. It's not to do with civil, but most likely computer modeling can be used to check such connections, right? Modeling So what you really do here, it's you're gonna be, there's different terminologies to talk about modeling, is imagining the intent you want to think about. Okay, so as I said, we're talking about the subject and what we want to teach you there. You're gonna have architectural drawings. If you're going to work with experienced team of architects, yes, they will know from previous jobs that the core need to be close to the center and with decent thickness. The wall of the core need to be with decent thickness because it's doing something, resisting lateral loads. And that will help you to also start thinking about it. So, and what you're supposed to be doing here is you can't build a building and test it. Yeah, we need to agree about this. Yeah. So as we're saying, some of the modeling people do is they're gonna build something in the lab and test it, right? If it's a small thing, like a small connection like this one, yeah, you can build this in the lab and try to put here and test and put some measurement tools and find out stresses and strains, and then do it by a computer program like ANSYS and compare it, and then say my theory is working or not working. That's if you are doing research. Same thing, if you, for a real building, you can do such simulations. Now, however, for a building, we cannot build a building, then try to break it. It's not possible. So that's why we have to imagine and simulate the building by softwares like the one we're going to be working on, RCB. But before we go this, I think literature can simplify things for us in terms of what modeling means. It can simplify things where it's saying we got two parts. One is physical empirical modeling, right? And the other one is theoretical modeling. So physical use, physical modeling means we're going to be using equations to describe the physical reality. And this is what we're going to be doing in the hand calculations, basically. This is what, at some stage, we're going to ask you to find forces. And the standards will help you to use equations. Those equations are coming from this part here. So there are equations like how we calculate force from multiplying mass by acceleration. This is physics. We know this equation. If you multiply mass by the acceleration, is going to be under. It will give you the full action on that flow. So basically, these are equations we can use to calculate loads. That's what we call it physical modeling. Lab testing is, as I said to you, you can build that model and test it, but if we're talking about buildings, this is undoable. We can't really do this part. Yes, we will be using this, and this is part of what we're doing in our hand calculations. Theoretical modeling means, again, we're still using mathematical models and that's what the phenomenon, which is in our case, vibrations or dynamic or earthquake. They're going to be several simulations and models we're going to go through. And the last part here, or the last type of under the theoretical modeling, is we use the finite element modeling, which you're going to be partially using because you are using RCB. RCB is still going to do meshing, and finite element means you are building a component and then cutting it into small pieces. That's what finite element means. You are building a component, you're going to tell RCB the column is this big, it's going to, or let's say walls, you know, the walls, the green walls, you tell RCB the wall is 180 thick and goes from this point to this point. So that's fine. You're going to say that to RCB. RCB going to cut it into pieces and then start stressing it and find out. You're going to tell RCB, this is my slab. Like, I've got example here. So if I just put, go to, I'm not sure if this is ready to show you, but let's say, no, I think this is not working model. I was just opening them quickly, just so you kind of build the concept. This is, you're going to be doing all these things, not now, in the coming weeks. So you don't need, this is a slab. the kind of dark blue area, it's a slab which you will define to RCB. Okay, tell RCB this. RCB will cut into pieces and then start. I'm not sure if it's already. Let me see if it's show mesh. No, it's not. It's not meshed, and it will take time to mesh it. So I don't want to do this now. RCB will cut it to small pieces and can mesh it for us. And that means it will convert it to finite element models. Okay. So going back to my notes. Now, what I can tell you, it's really, someone will say, are we using only one of those? Or it is a mix. And most likely in any project, whether you're doing a practical engineering project or you're doing a research project, it is really, there is no one thing to use. There is always a mix of this. If it's a building, you cannot do this. You cannot build a building and break it and tell us. Nobody will build a whole building and push it and say how strong it is. But it's always a mix of these kind of modeling practices, right? You're always gonna be using mathematical models to represent a phenomena, which is kind of, the process of using equation of motion. The first thing we will talk about next week when I start talking about theory is I will remind you about equation of motions. Remember the equation of motions? It simply comes from the force is equal to mass by acceleration. If there is a stiffness, you have to add the stiffness. If there is a damping, you're going to add the damping. You will see this next week. This equation, it is, because we're going to use it, we will definitely, and the software actually uses it, whether you or no. So that means we are practicing this modeling process. We will be using finite element, definitely, by RCB. So we're practicing this. We will be using equations to describe reality. So that means we're doing this. So by the end, the key, the summary of this page, you need to understand, unless you're doing a textbook question, maybe as some of our examples will be talking to you about a problem and asking you to find a value. So maybe in that example, the textbook example, we're doing only this. Maybe we're going to use a closed form equation to find a parameter and answer the question. Yes, that's where. But in the real project, and what you're going to be doing in assignment 1, you're ideally going to be doing most of those. And if you are working on a small project where you want to do some testing, then you will end up doing all this in that particular problem. So that's modeling. There's no one way of modeling or one type of modeling. The main definition of modeling is you need to simulate or imagine how a structure gonna behaves. Your imagination need to be as accurate as possible, so you're gonna be very close to reality and your work will be correct. Okay, and that's why when people or engineers design buildings, again, it's by the standards. They're always going to ask you, you must do dynamic analysis and static analysis. By the way, the hand calculations you're going to be doing in your assignment 1, which we started on from last week, is a static. We're going to use the static methods. So you can't do dynamic. It's just going to take, you can't do 10-story building dynamically. It's, you will see that it's undoable. We use static principles to work out the earthquake stresses, right? By the standards, I think one of the sections and clauses there clearly stipulates that engineers must check their work with dynamic simulations, and you can use something like RCB. Given that you use RCB, you will be implementing, you're going to use mathematical models because that's what RCB is built from. You're going to be applying finite element analysis because that's what RCB is about. So you just need to understand this modeling procedures. There are different pathways, but the general ones, you've got a physical event. We're talking here about earthquake, right? There is 2 ways, and by local standards, as I said, if you're working on earthquake designs, you have to do both simulations as well as static and dynamic. Now, if there is opportunity for you to build and check particular connection within that problem you investigate, then yes, you can do it, because it's gonna confirm your understanding and your reporting for the idea. If not doable like assignment 1, then we're gonna theoretically investigate it, but as per the standard, you have to use static method and dynamic method. Dynamic method gonna be the computer simulation. Okay, so after we go, you can see the physical model is it's just one step. You have to build the model, then put it in a test, then take measurements, then find out how things responded. If you're happy with the response, then your built model is good to go with. If not, you have to move it. A theoretical model, no, it's got more steps. First of all, you need to decide on the mathematical model, which, as I said, we're going to play with many of them. One of the main examples is the equation of motion. The main one we're going to be repeatedly using in this subject is the equation of motion for a single degree of freedom, and then we're going to expand it for 2 degrees and more over the weeks. So it means you have to know which equations you're going to be using, right, to define. Now, while you're going to determine the model you're going to be using, you have to make sure your problem can be also defined mathematically. So what does this really mean? Is the equation got 2 sides. One side are one side of the equation gonna be, I don't want to open week 3 lecture notes, but if I quickly write here, so next week you're gonna see, I will summarize it. You have mass involved in the equation, you have stiffness involved, and maybe you have damping involved. That's one side of the equation. There are other factors, like here we have acceleration, here we've got velocity, displacement, sorry, with the stiffness, and here we have velocity with damping or speed. This side of the equation is the problem. What's the problem? The earthquake. The earthquake will be shaking the building, and that's the challenge here, mathematical problem, how to simulate it. Okay, so, and that's, again, we're going to take you through the, what I was talking about last week, harmonic excitations, or you're going to have real earthquake excitation. So we need to define it. Now, how to solve the problem now, it depends on how complicated you've defined the problem. Was it just a sine? Was the vibration defined as a sine curve, like the harmonic motions I talked about last week? Is it just a sine curve or cosine curve like this? Then we can use analytical solution, which is by equations. We can still use math and apply differential equations to actually let us know how the building will behave, or the single degree of freedom system will behave under that sine or cosine wave. It is harmonic. It's just like going in the same trend. Now, if we working with earthquake, like really complicated motion, then we can implement numerical solutions, more advanced, which also you're going to be working on. So when we go through theory, again, it can have different pathways. They can be simplified, they can stay complicated, but really that's up to the engineers to decide on with practice and the trends, and you will be knowing what to choose as you go through the problem. Now, at the end, when you implement your solutions, definitely the results need to make sense. And this is again what we're going to ask you when you're going to be doing your hand calculations over 3-4 weeks. And after the break, after the semester break, we're going to let you work on the RCB. You have to, and you get some results from RCB. One of the questions assignment 1 is asking you as a group is to compare results and report about them as well. You need to compare the stresses you got from the software with the stresses you got from hand calculations, why they are different. You need to compare the dynamic properties from the software with the dynamic properties from your hand calculations, like the time period, right? So, and there is no one way to do this, just to let you know. That's just how we present it to the students. I think this is, again, I think I didn't, I think I mentioned to you that these notes were actually prepared by the by Inducta, which they, as a practicing engineers, they also consider this. Yeah, so there are different ways, but as you go with your simulations, you have to evaluate it, verify it. It's not one way. Like, there's no one flow chart to go through this process. You will experience all that with assignment 1 and find out how things can go. All right, challenges. We will talk about challenges, and that's part of the problem. One message, as a practical message to you, I would say about sometimes when a client approach you to investigate or design a building, you've got a group of engineers who are going to make it really complicated to, you know, expand their work and make it. And some other engineer will try to chop the time and say, no, I know how to do it with only, they may using only software. Again, you have to make sure you're going to be using the standards, because like sometimes engineers, they do shortcuts where they only going to take straight away when they got a job like the one you're doing in assignment 1, they're going to straight away go put it in the software and run simulations and goodbye. But there is a lot of hidden things can be picked if you actually get to do the hand stepping calculations as well. All right, so you cannot bypass information in order to win a job by saying, because you're going to be spending 1 month in doing it. Another engineer may say, I'm going to spend 2 months plus in doing it, because they're going to be going through all the steps. You always have to make sure what the standards want you to do. You need to do dynamic and static, because it depends on how high the building and which zone we're talking about, as you're going to see. Right, so the challenges, which, as I said to you, the question here, is it enough to simulate the vibration as harmonic motion, or we have to go to a real earthquake excitation? So are we dealing with non-existing structure, a non-existing event like earthquake here? Now, earthquake simulations is really, we are using simulations that have been developed by standards. We don't know how the next earthquake will come. We don't know its magnitude, right? We know how the new building gonna be built, but nobody knows how the earthquake gonna come and hit the building. All right, that's why there are the challenges. There is, you need to switch on that imagination side of your engineering skills. There is no equations or step-by-step guidelines to let you do this. Sometimes some of the steps may be bypassed in a project, but you have to go in another project. For example, if your core was in the center in a project, you then can follow steps. However, if it was excessively located at a corner in your building, you have to go through a different process, right? And then if the core itself was symmetrical, it's different than if it was not symmetrical. If your building uses a block wall, it's different than if your building uses precast panels, because precast panels got mechanical simple bolt connections, but block walls, no, they can be well engaged into the. So there is challenges there in terms of predict the structural response. How, yeah, and that will come with, that's why there is always a team. There are different engineers to be checking on each other. And yeah, experience typically. There are a lot of buildings standing, and many thousands or millions of buildings standing outside, and they resist such actions very well. So the theories worked, and it's not impossible, but we just need to make sure the correct checks have been done. Okay, and I think what I said also covers this point here. There is different loadings, especially when talking about buildings. And what I said to you last week, you have to combine those loadings: dead load, live load, wind load. When we come to wind load, there is north winds, south winds, east winds, west winds. On top of the earthquake, you don't know from where it's coming, whether it's coming in the east side, north side. There are standards which tell us how we're going to combine things. So it's not only we have to combine it once, we have to combine it with considering different cases, different scenarios. That's why we're going to have 10 cases to simulate. Okay. Computer simulation, computer model only as accurate as the equations. So it will be basically doing what you tell them to do, right? It's like a calculator. We use calculators to get more accurate, correct results, right? Same thing. So it's just a calculator. It's not an engineer, right? Whatever you gave them, they will reflect correctly. And I do expect some of you will come very up with very odd differences between the computer and your calculations, but that's what you need to investigate. Maybe you have told the software that the connection between the wall and the slabs are rigid, but they are not. Okay, so we will be sensing these kind of differences as you go through the exercise. Now, as you're going to be doing your first building, these challenges are going to be high. As you're going to be doing your fifth one, those challenges going to reduce, right? But you know, with having more complicated architectural layouts, things will be more and more complicated. So two major aspects. I think at the start of my introduction, you know, when I start asking you what type of software you use, I kind of covered these notes here. When I was asking you what type of software you use, some said SpaceGas, some said STAT, some said some mentioned as well. What was it? ETABS as well. So that's really what we're talking about here. There is different type of models. There is the 1D, there is a 2D, there is a 3D. All right. So that's talking about building the models. Whenever you go this way in the line, it will be more complicated. It will take more time for the computers to solve. But nowadays, it's easy to access high-speed computers enough for such jobs. So it's not really a problem with the speed of computers, but it's with these issues, with the challenges, how you're going to be simulating things, you know, the thinking you need to put to get it fed correctly to the computer. Examples of aspects we need to consider when you do the structural modeling. The columns, are their ends rigid or pin? At the top of the column, is there a header beam or not? So this makes difference. Okay, so again, if we're talking about 20-story building, this needs to be carefully done. Right now, one of the good functions with RCB is they got those copy mechanisms, which really, if you do something on one floor, you can simply repeat it on the others, which is very helpful because you don't need to keep doing these checks for each floor. All right, here we're going to have kind of 10 stories. Yeah, so if I quickly show you where our tools, 3D, hopefully this can just show me the approximate look. Yeah, this is kind of how your building look like. It's missing some features, but we don't need to worry about them now. So that's what I was talking about. There is basically you can build one of the floors and build it correctly, put the loads correctly on one floor, and then by a few other clicks, you will be able to build the rest. But, you know, nowadays architects can get things more complicated where you can actually need to spend more time on it. So maybe they don't have such similarities in the floors for other buildings. Okay. Back to our notes, how to model the soil. Yeah, that's again, things you need to consider or an aspect you need to consider. Whether typically there is a closed form equations which are built already in your like it's already built in RCB, we won't really worry about such things in our problem, because in your problem, we're assuming your building is sitting on rock. So you can assume it's just a pin connection, it's not a problem. But sometimes if you've got soft soils, you have to model them as spring, and that's need to be thought about. This will take from you maybe 2 days to actually go through all the investigation to get it right. Stiffness of the elements, which we will start talking about in the theories from next week. Stiffness means how strong are the columns or the walls or the core. The main guy here to resist earthquake in the building is the core, which depends on its shape. So if the core was complicated, we have to model it as accurate as possible. And RCB, it's very simple to do with RCB, which you're gonna see when we start doing it. All right, there are other things which you will experience, many other aspects to worry about as you simulate and build your software with RCB. So this image here really kind of gives you an idea. You know, I said to you at the start, I said to you about 15 or 10 years ago, I checked a building that was a building. It was 20-story building, or I can't remember how many floors, where they checked their earthquake loadings and behavior by 2D sticks. That's it. That's what they did. And the building is built and it's standing now and everything is perfect. So it does work. It does work. Okay, it does work if adequate effort were made. And as I said, they use something like CIV5DSD or space gas, but they have really detailed information. It's not like as a stick, as you can see. You know, if you go to space gas or ETAP and click on that line, they have defined things accurately. They have told that this element got the correct engineering properties in terms of its inertia, the elastic modulus, the concrete properties, the dynamic properties. They have been all studied on different sheets, like by hands or whatever they used, and then they fed it to space gas or CIV2000. Then they asked CIV2000 to consider some harmonic excitations or consider some spectrum analysis, and then they ended up determining the deflection of the building, the moment of flexure on the building, and shear on the building. Perfect, job done. So it is possible, right? Now this package, it seems to give you, so it can be done here, but this package that we have, it's kind of, they jumped a step where, as I said to you, to embed the local standards. That helps you to, by doing a few clicks, to calculate the wind load. Now, in this case, you have to calculate the wind loads, you know, manually. You have to calculate earthquake loads manually. You have to apply spectrum analysis manually to do the static calculations. But here, with this package, you will have everything inbuilt, and you can actually do the 3D. This will help you definitely in case your core was sitting off the centroid. Then the software should be able, if things have been modeled correctly, to take those extra twisting torsion actions on the core. Now, if this have to be done manually as well, if this was a case, and then you apply the analysis. So in some building like this, you can do the right side or the left side. They both can give you an answer, but one of them can take you to your target quicker and can do many other activities, answers with better visualization, etc., etc. Because that if things have been correctly, then you may end up supplying more economic drawings to your client or builder. So with such softwares, you can easily, like for example, let's have a look about this stress contour, right? you can see from looking at this line, you will be able to see I have here excessive stresses. Stresses will get lower as we go up. Then you can quickly determine I need heavy steel here up to this level, then it will be reduced up to here, then it will be reduced up to there, etc., etc. You should be able to manage this process faster than doing it manually because you have to do this by hand calculations, right? Because here the cantilever height will change from one case to another. Okay, so this is again different ways can work, but some of them can take you quicker and you can have advantages from packages you may employ. Structure. So some of these nodes and images I may have already talked about, but I'll just visit them quickly again. Where are we now? So we finished about 6. Let's have a break, maybe 6 minutes break, and then I will just continue. Now, someone may ask how you need to learn from these notes. This is kind of a preparation for you to know what computer simulation, how you're going to be using it in this practice and in the future if you're going to be using it in a company. Will you be asking the final exam from those notes? I will be very clear with you. The answer is no. I will not ask you to list these things. I will not tell you what does define for me the modulation. No, the modeling, yeah, you will not be asked like this. I just want, because sometimes you can see engineers, they think that the software will do the job to them. They think that the software is another engineer who's if you give him few inputs, they will get it right. And the colors, if the colors look nice, that means okay, job done. The answer is no. There is challenges, there is issues, there are checks, and that's the key message. So yeah, that was just again a preparation for assignment 1 and the use of simulation. So you also need to be accurate when you do the steps we're talking about together. And one of the points I mentioned to you, consider the dead weight of the walls for your assignment. Because when you're going to simulate this in RCB, you're going to physically put walls. And I do see students in their hand calculations, they did not count for walls weight. In the program, they did. That's why you're going to see big differences there. Okay. So let's have a break. How many minutes you want the break to be? 10 minutes? Yeah, since you said it, that's fine. So we'll meet, yeah, just after 10 minutes now. Yeah, just 17:317. We'll see you then. Hello again, and let's keep going with our computer simulation or structural modeling notes. So far, we covered the challenges that you would face with simulations, and also the type of simulations, like the main types of simulations engineers can undertake with computers. They can be as simple as sticks, like SAP 2000, and then go really advanced to something like ANSYS. RCB, the one that you will be implementing and using, it's kind of lower level of ANSYS program, because it's got its own blocks to use as an element in your building. So here, yeah, I've briefed you about such thinking. Usually you will be looking at framing up a building, right? How it's actually standing. Architect drawings will give you an idea about the look of the building, whether elevations or plan views. They will give you an idea where the staircase will be located or the lift. That's typically agreed in the building industry. That's where the structural core is located. So your thinking should be something what the red lines are showing. Sometimes in buildings, if they are really large in terms of a plan, a footprint, then the cores cannot do the job. If you got 30 long meter and the core was not really available, like few of them, if you got 30 meter long building, you would need three, a core maybe is located here, another one there, and maybe another one there. Sometimes you'll find it's really not adequate. If this is not possible, let's say we don't have one here, we don't have one in the middle. That's what I was saying. If we don't have one in the middle, then that means it may not be enough to stabilize it, but by two corner cores, or they may not be large enough, etc. Then in this case, you may end up required to use portal frames. Okay, so something like what we're seeing here. Your concrete beams and columns will be engaged together in a way where they all act as a portal frames. And I can tell you, such simulations cannot be done adequately by RCB. You're going to need to go back to space gas or SAP 2000, because it's going to be sticks, something like what you have here. So these are, you can consider them as considerations that you would need, and decisions you need to think about from day one. Yeah, and then you will be employing a calculator. Yeah, some people call it computers or software. So it's a calculator in the end of the day. Then you will get results. But ideally, you would need to think about the problem. I think this image, or this slide here is taking you through what I was talking to you. This is the actual structure, what any client or the common people can see. The developer, the owner will look at his property, something like this, but you will be thinking about its structural system, and you will be making sure the system should cope with lateral loads from, as I said, knowledge, what you're doing now with the course, and experience. Experience does not mean you have to always sit for 10 years with an office, is do many actual authentic examples. And you kind of stepping into this when you're going to be doing assignment one, because it's almost very close, or it is actually close. It's a real building, but it's kind of simplified a bit just to avoid all those irregularities that engineers typically have. I can tell you sometimes engineers can simplify also the buildings they're looking at if it is not worthwhile, because sometimes when they look at a building, they see they got enough cores already and it will work. And the architect already wanted 3-4 cores in a small building, because he just wanted it like that. Okay, so you're going to say it's going to work. So you can actually simplify it and get it to work, because it's going to be working. You don't need to go and make, usually engineers would go through very well defined calculations if the problem was challenging. The problem is challenging, and you want to use the cores up to their limits, because if they are not working, as I said, you may think about portal frame, if possible. If not, like what I said to you in your assignment, you have to introduce some additional shear walls if the cores are not enough. Okay. And it's going to be a cycle. It's going to be a cycle that the results going to come back to you to review until you get it to work, like any design process you did with structural engineering, like concrete. Right? See, this is the message I kept kind of bringing to you, and you always need to consider this message as you go through assignment 1. There is no book. There is no steps to follow. No one steps. This is kind of the beauty of structural design. You know, you can hear about AI, artificial intelligence, and all these kind of things which get job done in many research activities, or this is not really possible. Yeah, because you can't give, go find one of those websites and ask them to design a concrete beam as per standards and see what they're going to answer you. They won't tell you put 3 bars at the top and 3 bars at the bottom, and they can't do this. And imagine now we're talking about one beam. What about if you're going to give them architectural drawings? I'm not sure how you're going to tell AI designed it, and each architect is doing it in his or her own way. So it is fun, and there's no one steps to do. You need to consider that as you go. Awareness of the issue, understanding the principles and underlying theories. I would say not only one theory, there are different theories to consider. So education and knowledge, you always need to mix things together. And it's not a cookbook, it is about training and skills and doing more examples and getting the right answer. Types of structural softwares, which I mentioned, but we're mentioning it here again. Space gas, which is equivalent to SAP 2000, and there's another one locally used, microstrain. That's for frame analysis, which, as I mentioned to you a number of times, one-way beam software. It's a wrapped, locally used wrapped software. It's a one-way beam slab. Finite element softwares, which are the advanced one, like ANSYS, Strand. That's why I was asking one of you guys, Strand. And as far as I believe, they conduct those very finite element meshing and analysis for deep details, for connections, for bolts, for all these things. Problem-specific inductor and computer systems. So this is a problem specific. So the software we are working on, it's kind of by the industry, by inductor, they consider it as problem specific, which I would agree, because it's designed for buildings, right? They know in buildings we have columns, we have walls, we have slabs. So they gave you that feature and element clear in the software, and you're gonna see how handy it is, right? Space gas, not sure, or SAP 2000, they say this is a beam, so it's a stick element. This is a plate. They don't say it's a slab or a wall. They just say it's a plate, and it's up to you how you're going to use it. You're going to use it as a wall, or you're going to use it as a slab. And then you have to go through all the actual setups to let it behave as a slab or a wall. While inductor or RCB, the one you're going to be using, you just need to say this element is a slab, and then inductor will look after the actual behavior because it's established there. All right. And ETABS is, as I said to you, is part of the CSI ETABS. So as I said to you, ETABS is something similar to inductor. Okay, so frame analysis, what we use for where do we use space gas or SAP 2000? We use them a lot in structures like these ones because we have sticks here. Yeah, nobody would use RCB or ETAPS to simulate such problems. You would think about using space gas to simulate such structures, and then you start again. If you're going to simulate this in space gas, don't think you're going to make a click and answer. You still need to say space gas. You need to tell space gas or SAP 2000 how the wind load going to come into the portal frame. We're going to have east winds. Sorry, if this is the north, we're going to have north winds, south winds, or you may have east west winds or east winds. Yeah, all these kind of actions a human being called a structure engineer is required to think about it. The software will not do it. I think if you practice things with SAP 2000 or space gas won't be able to do all these kind. There are, I mean, some engineers are trying to simulate things, but they will always give it to you to double check. So you always need to build those case studies, the situations, and work out the worst case scenario. Work out, and on top of external actions, there's other cases where you're gonna be assuming the door is open and then the wind can come in and then cause some uplift pressure. So this is kind of saying what you're gonna be doing on your core. You're gonna consider different directions. On top of the wind, you're gonna consider earthquake as well. Okay, that was to do with the frame analysis softwares. One-way beam software, that's similar, as I said, that's what we do with wrapped or same package. I was saying there's a SLB slabs, which is produced by Inducta. They can, with such softwares, you're only gonna look after floors. So you won't worry about buildings like a 3D, you're gonna worry about a slab, and you can use them to design band beams, to design slabs, whether they're bending actions or their deflections as well. Yeah, like slabs supported on beams or beams supported on columns. These can be looked after by one-way beam software. When we say beam, the beam can be a slab or an actual beam. So there's always strengths and weaknesses. Strength engineers are familiar with the concepts, easy to visualize, and fast to get results. Weaknesses, many assumptions must be made about load path, right? There is assumptions, and that same thing can happen for your RCB as well. Assumptions of actually neglects capacity in the second direction. So even here, if it's a one-way slab, there is always actual capacities in two-way, because you see here, there is always, because the computer will take this as one way. It's just a computer because the equation told him to do that. But in reality, there is also some strength and some support running in this direction. So the pink color, the pink, will definitely be simulated to span up down the page. That's it. But when you're gonna pour this concrete as a diaphragm, one single gray material, no, there's gonna be some resistance in this direction as well. But nobody will you have to use the package to do that. You cannot use those one way because it's a one way. It's just telling you what's happening in one direction. It's not telling you what's happening in both until you use finite element, and that's what we're talking about here. So this is how finite element works. This is the actual architectural floor. Then you will take it and place all your columns and walls, and then specify your slab, right? Then you click and it will mesh it. It will divide it into elements, finite element units. Now, this software will be able to deflect and flex in both directions. Depends on how it's supported, and that's where we can have more accuracy in the design. In this other one-way beam package, no, we're telling the slab you're going to be flexing this way. Goodbye, that's it. But in reality, we have also some support. So it's kind of more economic solutions can be done with softwares, when they're going to apply finite element modeling. Now, again, the kind of advantages, the finite element technology is used by these softwares for building purposes. So it is a problem-specific software, but it's advanced, or kind of, advanced would be the best word, advanced to the level where it's able to divide its structural components into small pieces, so the slab can be correctly reflected and it can be economically engineered. Okay? And that's kind of the advantages behind packages like ETABS and RCB. Right? Now, not only that, after you mesh it, obviously, we're going to do kind of meshing. You can make other clicks and the software will start giving you these contours. These contours can represent the bending action. So here we have positive bending, obviously, because here we have columns. This is column, this is column, this is column. The whites, they represent a void, like a hole in the slab. So it's not column, column, column. You can see the blue means, I would say, mainly it would be negative bending. Negative bending, this is positive bending. And as you're gonna, now I will not, it's really up to you if you're gonna practice slabs, you may be able to access it somehow. But in our exercise, we don't want to teach you slab design. We're teaching you dynamics. So we're gonna look to buildings. Okay, we won't be looking to floors. But I'm telling you the difference between using elements rather than using sticks. This is sticks. This is using one-way beams, and this is using elements. Elements will give you more accurate results that will end up letting you choose and document economical designs. Now, weakness. That's the weakness. Results may be difficult to interpret, correct? And it is, if you don't know what you're doing, if you don't study correctly, if you don't have the two things I was talking about to you, or the lecture notes, where is it? Where is it? Here. If you don't have enough training, if you don't have enough education, then those softwares, they are simply just black boxes. You don't know what does it say. And if you bypass some steps, they can go wrong. So this is something you need to consider. And the strength is basically, as I was saying, it will end up giving you economical results. So that's just a table that Inducta put up there, just to kind of tell us how problem specific, what's the difference between problem specific and pure FEA. Pure FEA, they are like ANSYS and STAD Pro. They are very good in analysis, but they don't have design packages inside them. They open like very generic softwares. You have to go and think about the standard limitations. Okay, and they do have manuals to design things. However, the problem specific, like RCB, they are they conduct analysis and they are integrated with the designs, but in some of them you don't need manual design because it's already inbuilt with them. They're already inbuilt inside them. Okay, but given that, as I said, you're going to be doing for your RCB, for your assignment 1, you're going to be doing the hard static calculations, and you're going to be doing, so you covered this gap. You're already going to cover this gap because this week and next week, or this week, you're going to be doing the wind calculations, and next week maybe you're going to be doing the earthquake calculations. So you're actually going through the design manuals. You're going to be doing this, all right? If the if this was not achievable by the software. All right, so yeah, structure modeling using software. You're going to input things. I think you have received this message. Black box computer. Yeah, if you don't know what you're doing, which should be prevented. And to overcome this problem, you need to check the outcomes. The outputs need to be evaluated. It's always a good practice not to check the very final results. It's also good to look at the results you may achieve in the middle. For example, in a team now, you are calculating the earthquake, or like you're calculating the dead load, etc. At some stage, we're going to be asking you to calculate earthquake lateral loads on each floor of those 10 floors. While you're going to be building this model, there are some steps where you will ask inductor to do that calculation as well. So check that. Don't go progress with your modeling to the end, and then you may be finding some errors at the end. It's good to do that. So once you calculated the earthquake loads on the cores in RCB, compare them with what you've calculated manually. Once you started estimating stresses, compare them with what you did manually. Once you get the dynamic behavior and response, so this is really would make you understand how these black boxes work. Okay. There are statements here. Why softwares can be considered to be black boxes? Because it's complicated. Yeah. And this is really all about what's happening with RCB. RCB, we're going to show you in week 11 how 2 degree of freedom systems can be analyzed and how to estimate deflections and vibrations. But when it comes to 10-story building, your equation, you're going to be a matrix made out of 10 by 10 columns and 10 rows. So that's how the matrix is going to be 10 by 10. I don't think you will sit down and do it. I don't think you did at math courses as well. So nobody would be thinking about it. You need to have some engineering judgment to rationalize and understand the results as well. Implementation is complicated. However, the packages with softwares are over time, they keep advancing them and simplifying them, and that's why we're trying to give you an experience with RCB. Okay, so must be used with computers. That's very clear. Some technologies are still not accessible, but at 2023, things are getting more accessible than before. Insufficient education. Yeah, people may rush. They may have a good opportunity for a project and they just want to do it, but they don't have engineers who have been at least practicing or knowing how things work, and then they may not be able to use those packages, and they may end up going to very simple processes, but like simple steps. But then this may not be sufficient to get economical answers. Okay. But I think with the practice you're going to be doing, you will be touching on these kind of skills. So you're going to sense how complicated. Yes, they're going to be a group of students who will not get the numbers to work close to each other. This will happen. But if you have researched it and if you have explained it, that's enough for your assignment. The numbers are supposed not to be accurately 100% accurate. Some students will get it, some students will have reasonable answers, and we're going to be discussing this as we go for your project. Okay, so yeah, we do have a group of engineers who are still comfortable with what we do, what they're doing before, and because they don't have that confidence, right? The confidence will come from comparing results coming from the softwares with hand calculations. Okay, and if this is done for about 5 projects, things will work very well from there. Design codes, which you will be working on, making things more confusing if people haven't been using this. But you're gonna actually sense this mix with assignment 1, we're going to overcome this problem. It won't be confusing. You're going to know when the design code. It's one of the things I tell when we teach codes to students. They are not guidelines to tell you step by step what to do. No, they just tell you how design attempts need to be standardized. It's like kind of the engineers are trying to have an agreement about what factors to use to determine earthquake in a Melbourne-like area. There are many factors. If you are designing a building in Melbourne, you have to use this factor of acceleration. If you are designing over a rock soil, you have to use this spectrum analysis. So that's what the standards does. It makes sure engineers who are going to practice in this area, under this environment, they have to all use those parameters. And by law, you have to use them. If you did not, then you did something wrong with your license. Okay. In terms of whether you're going to use your hand calculations or you're going to be using your software, it's not legalized. Yeah. However, whatever you use, they have to be correct. Okay. Now there are standards, as I said, saying do dynamically and statically. Dynamically, there's no way you can do it by hand. If you want to do it by hand, go do it by hand. But I think you're gonna you're gonna spend all your time doing math, and they're gonna build a building and you're still doing the math. So it is, yeah, that's where you need to train and know the softwares, evaluate them. Remember, all software suppliers, regardless how confident they are with their software, they're gonna say, whatever you're gonna get from the software, it's your responsibility. Yeah, like this software, again, they do have very excellent real practical training videos, which I shared with you, and it's for your own use. In terms of the assignments, I just want you to follow me what we're going to do over the workshops, and I will do my own video. When we're going to get to the stage to build your building, I will show you kind of a simplified steps. You know, the videos that, like here we go. That's I've given you this link in LMS week 2. These kind of, they are really excellent videos for practicing engineers. Look at them. I'm sure you have the time to look at them. They go through a lot of perfect details, and you're more than welcome to use them for your modeling. Now, in week 5, 6, I will build this building for you, or I've actually have a video already, which shows you how to build it. You can use my way, or there is, I kind of just gone like kind of bypass some detail because I'm not explaining to you. I just want to show you how it's built. The training videos, they take you through issues that may not be the situation we have in our assignment. So you're more than welcome to look at them. But let me highlight important sections, like which I will mention to you later on, about sections which are related to frequency analysis. Here we go, frequency analysis section. This is very useful for your assignment too, because after you build the model, after you get something like what I just showed you here with this, I think still it's not 100% complete. So this is the building you're going to be building, which is fine. You can see my video, maybe it's about 20 minutes or so, and by time, if you did it once, I'm sure next time you can do it even faster. All right, but the issue is you need to conduct dynamic analysis because we need to get the natural period and the p-value and the t-value and the mode shapes, right? They are carefully detailed here for you in this section, frequency analysis. Now, this is not something you need to do this week or next week. This is something you're going to be doing after you do the hard calculations and submit the work. Remember, assignment 1 going to be submitted at 2 main stages. Number 1, when you're done with your hard calculations and design the core partially, then you will have another 2 weeks to simulate and work on your RCB. You're also going to have the break, the term break, to work on that as well. So you should be fine there. Okay, and we will talk and this kind of. So quickly going back to my notes. Yeah, so how to deal, yes, you need to, as I said, the standards, you will experience that as we go through, and you've already experienced that, didn't you? When I ask you to find dead load or life loads, we have to follow what the standard is telling us to use. That's like a very simple example. I already said to you life loads for office buildings going to be 2 kPa, so that means you already follow the standards. Okay, then standards will be a bit more detailed when we get to earthquake loads, which we're going to do this week or next week. Wind loads. I said to you, we're not going to show you all the details of windows. We're going to use our, another kind of program. And that's, again, you are considering the design codes in that. All right. Now, the notes here are telling you sometimes softwares, they design things based on codes, and the codes keep changing. Yeah, they keep updating the codes, and sometimes the softwares don't update their packages, and that's some problems people may use. Yeah, sometimes codes are not possible for some complicated buildings. That's where engineers will make their own expertise in it. They can, and the standards allow you to do this. If there is something you want to do from theories and it's still going to make the building safe, do it, no problem. And a lot of things like this would happen for earthquake design or even static designs. Yeah, so typically that's what we're doing. We're starting with a simple, like with our static steps we're doing together in the workshops. We're going to be simplifying the model as a stick and working through it to understand the general behavior. And that's what engineers would be thinking about before they're using a software. Okay, before using the software. This is also important note, iterations. Several iterations for a structural model as the design progress. And maybe here you're going to be doing one because we're asking you to compare results with the software. If things does not work, you need to investigate what were the cases and readjust your model, then analyze it again. So maybe you will get the right answers. Maybe you need to do another iteration. But in my assignment, I'm not asking the students to do more iterations. Just do the steps and compare and report the differences regardless how you find them. So you will in assignment 1 understand the structural response behavior, and we started working on this. Sensitivity analysis, yes, we will do this. We're going to compare results with hand calculations, simplified hand calculations. Yeah, we're going to compare it and that's what you're going to experience. Does not always match complex models. Yeah, so FE versus stick cantilevers. We're going to see that, and we're going to come up with the reasons why did that happen. And then you can justify why it's acceptable as well. Okay. Start with simple and increase complexity. Yeah, that's also something you can always practice. Now, the building that we are working on already simple, so we don't need to worry about this. I've already, assuming we have one core. I remember if you look at your architectural drawings, you have more than one core, but we're just going to work on one to start simple. Some results, yes, cannot be checked, but can be judged on. So if like there is element, you really don't know how to model it because you're worried about how it's going to be stressed. So the best approach there is to remove it from the simulation to be safe. The best thing is to remove it from the simulation to be safe, and then you can check it statically. That's what we typically do. If there is a special feature or special arrangement, you don't want it to take any load, you don't know how to simulate it, then just don't put it in the model, and then you can, when you detail it on your drawings, just let it be supported on the building. Don't let that element supporting the building. So consider it as a non-structural member. In other words, consider it as non-structural member. Okay. So basically today's lecture, it was just kind of switching on your, I think I missed maybe some of the, I think I missed this one. Yeah, which kind of summarizes, that was just the lower slide in the one before the last, which help engineers, which type of software should they use. There is the questions that are not really answerable, like you cannot really answer which software is better. There is no better software. As I said, they all can do the job. Depends on the situation. Sometimes space gas or SAP 2000 is the best. Sometimes RCB is the best. There's no question like which one is accurate. All of them should be accurate. All of them is a calculator. They should all give you correct answers, but they need to be correctly read and investigated. Is there an easy software? No. Also, it's not a good question. There is no easy software. It again depends on your experience. Same thing with cheaper, or it does not look like they all, if you're gonna look into their details, someone is a bit more expensive because it gives you something else. Maybe you don't want, then don't buy it. That's it. If you don't want that extra facility in it, then go get the other one. All right. So the key answers, the key questions you would ask, the type of analysis, which we talked about, what we do, what's the problem, how we need to simulate it and model it, the modeling speed. But I can tell you, even with this nowadays, a small computer can do really, they got many cores and very fast. Typically, finite element models 20 years ago is difficult to put on a laptop because they're not that fast, or they got heated a lot. Nowadays, you can put ANSYS on any software, on any machine. Complexity, familiarity, this is going to come with time. Widely acceptable, this is really important. You need to use a software which is locally acceptable. You can't use something, because remember, whatever you're going to do, whether drawings and documents, and other engineers will check it. You don't need to use a software nobody can access. It's going to make life easy for the project, which is going to make you, get paid quicker as well. Integrated design, the software which does many things, like the RCB, you can calculate the standard actions from the standards. You can look at stresses. You're going to see that you can look at dynamic responses, vibrations, simulate other actions. Okay, so yeah, I think that was the key message from today's lecture. That will be the last generic lecture we have, the second one, but from next week we will be talking about the theories. So we're going to have kind of more consolidated topics followed by examples to do. So typically the lectures should finish within 1 hour plus, and we will have examples where I actually want the students to work with me on. The solutions are there. Some steps needs to be calculated. So hopefully next time, guys, you can have calculators with you. So during the lectures, we do some calculations at the end. Depends on the time. And that's it for today. Okay, any questions? Stop recording.